Carlos Formoso.
Good morning, everyone. I'm going to present this paper, which is based on the work of one of my master's students, Fernanda. And this is one of the studies that we've been doing, exploring the synergy between Lean and BIM. So it's about logistics in prefabricated building systems. And in the study, we're exploring specifically concrete prefabricated systems. And we see those systems as engineered to order production systems, which has some important characteristics. So the customer order is placed at the design stage, so the company prepares a plan without knowing exactly what the product is. There is, of course, uncertainty related to the assembly process, especially because it interacts with other processes on site. You need to coordinate and synchronize different types of flows like design, fabrication, logistics, and assembly, which makes the process complex. The lead time, of course, it's a prefabricated system, needs to be short, and some resources are shared between different projects. So typically these companies work in a multi-project environment. So although the aim of prefabrication is to make things simpler, there are some types of complexity that exist, which is related to the uncertainty, to the interdependency between different tasks. So a typical situation in companies that deliver prefabricated systems is that they neglect this type of complexity. And as a result, for instance, companies, they have different planning systems, one for each phase, and those planning systems sometimes do not interact properly. Assembly becomes unreliable. So there are many delays in the delivery of components, and there are some problems in terms of integrating the parts. And you see in many companies in this sector, you see lots of inventories. So you see inventories in the manufacturing plant, and like in this example, you see inventories in the construction site. You can see that the inventories are larger than the building itself, and this, of course, tends to add many non-value-adding activities. You can damage the components when you move them. And of course, the lead time tends to increase. So this is probably one of the reasons why some companies find it so difficult to use prefabricated building systems. So the aim of this paper is to describe an application of BIM for the modeling for supporting the process of planning and controlling logistics operations in those systems. So there are some important assumptions. The main one, assembly should pool manufacturing and design. So you produce components according to the demand from the construction site. Of course, you have a master plan, but sometimes you need to make some changes in those plans due to uncertainty, or sometimes due to client demands. You should eliminate as much as possible transportation, operations, and storage. This is relatively obvious, but in prefabricated, concrete prefabricated building system, this is really important. So the idea is that you get the components from the trucks to assemble instead of storing them on site. You should only have some small buffers. The idea also is that you need to design and standardize logistics operations, right? So many companies focus the standardization in value-adding activities, but you should also do that for logistics operations. And in an environment in which you have so much uncertainty, it's really important to share information about the status of the process. And this is really, really important. So we developed, one of the empirical studies was in a university project, a building that was a group of buildings that were built for a university campus. It was a very challenging process due to some characteristics of the process. There was lots of excavation in the construction site, and the site was very much confined, and the components had to travel a long way, more than 700 kilometers, because that was where the manufacturing plant was. So these are some pictures from the site just to see some of the problems. So the trucks, they had to go down, a relatively steep slope. So we did an action research study in that project. So we interacted with the company. We introduced some changes in logistics, in planning control. We implemented some lean principles and some 4D models for supporting decision making. And we explored the integration between logistics and the last planner system. So the idea was to have, similar to the last planner, to have different hierarchical levels of logistics management. In the initial process, they had two important sets of information. So one was the logistic plan. So there was a plan of batches to be delivered, sequence of components to be produced, and another important information was the status of the component. In order to demand the batches to the construction site, the site manager had to know if the component had been produced, if it was stored in the manufacturing plant, and so on. So there was a difficulty in terms of keeping this information updated. So the first step was to devise first a 3D model of the assembly process, and then a 4D model. The company didn't have a 4D model, so we had to develop that in the project. And then we, in the 4D model, this 4D model was updated several times according to the constraint analysis, so according to look-ahead plan, and also using feedback from weekly planning. Something that was very important, we defined two confirmation points. A 15-day confirmation point, 15 days before assembly, confirmation point for producing the component, and another confirmation point for delivering the component, right? So only after that, the component was actually delivered. And we introduced some degree of automation in producing information about the process status. And this was a combination of information updated in the BIM model, like the batches, the sequence of batches to be assembled, and also information from the manufacturing plant about the status of each component. So this made much faster to update that. So the main impacts of the study: logistics, planning and control became much easier. So there was a 32% reduction in the time spent to plan the delivery of batches, which is a benefit. The status information was made available in real time, so it was very fast. So there was daily updates of status information. And all the information needed for logistics planning was in the same table. So that was a benefit, avoiding mistakes when processing information. In terms of the assembly process, there was some improvements. 95% of the deliveries in the construction site were on time. We didn't have information before we implemented that. Okay, I'm finishing. Because it was so messy, the planning process, that they didn't know what was the percentage of deliveries that were on time. We increased productivity, you can see, from 18 components a day to 39. And in the paper, we talk a little bit about the main contributions, which is about how to integrate information from the BIM model and process status, the definition of triggers for pooling production and delivery of components, guidelines for standardizing logistics operations, and the connection between logistics management and the last planning system. Thank you.